Is that better? Okay, so what about this? This is the last. This is the last page. Any questions about that? Is it clear why the rate for this reaction is the same in every case? I mean, that was one of the questions you were supposed to answer, right? Provide the rate expression for each of these reactions, and we're starting with the same enantiopure tertiary alkyl bromide. We have different nucleophiles. In the first example, we have ethanol. What is the product that we're expecting there? Is this an SN1 or an SN2 reaction? SN1, how can we tell? It's a tertiary alkyl bromide. You will never do an SN2 on those. They're too sterically hindered to undergo an SN2 reaction. And so it's going to be an SN1. But what is the product? What is her nucleophile? OH? Only OH? I don't see any hydroxide ion here. I see ethanol. And so this is where pattern recognition comes into the picture. The pattern recognition, if you recall, the previous lecture we were pretty much discussing. Were you able to look at the slides? In the previous lecture, we were discussing a solvolysis reaction, in which you have water as the nucleophile. You get an alcohol. But now we don't have water, we have ethanol. This is the pattern recognition. What is the product here? Okay, we put the scaffold. What is here? Anyone, please. Otherwise, we can just keep staring at each other. Huh? No. There's no hydroxide here, and there's also no water. What is the nucleophile? The nucleophile is ethanol. So what are we? If it were water, then it's OH. Fine, we remove the proton from water. If it was sodium hydroxide, would be OH. It's already hydroxide. If we have ETOH, we're basically substituting one hydrogen in water by the ethyl group. So the product that we should be expecting, and in fact that we would get, is an ethyl ether, right? That is as simple as that. You have to be able to recognize the patterns and be able to see how ethanol can be a nucleophile because of the lone pair on oxygens. That's enough. It's pretty much like water. And then that proton gets removed by the same ethanol. And so if we were to do the stoichiometry, at least we need two of this so that we can generate as byproduct but organic chemists, we are organocentric, and we usually don't tend to write down the inorganic salts or the bromide or whatever it comes as the byproduct. But what about the rate of this reaction? It's an SN1, so you should have come up with the following: the rate constant times the concentration of your alkyl bromide. The concentration of ethanol does not play a role in that rate. How about the percent EE? We started with an enantiopure or pure isomer, the R isomer. You could say it's 100% that. 99.99999% EE, or 100% EE, if you will. What is the percent EE of this product? Do we get inversion or retention of configuration? And how do we call that? Racemization. So 0% EE, and this is a racemic mixture. We get the racemate of. Now, if we have N-butanol, the product that I expect all of you to come up is O, Bu as butyl, and ethyl there. And of course, racemic. So that means you have both enantiomers. The rate of the reaction is the rate constant times the concentration of your alkyl bromide. 0% EE again. This is what racemic means. If you have a racemic mixture, you don't have any excess of either of the enantiomers. And in an exam, if you write this with no stereochemistry, you would only get points if you indicate that this is racemic. If you leave it blank or you don't specify that it's racemic, you would not get credit for that because you're not indicating stereochemistry. The other option is that you draw both enantiomers and you indicate you get a 1-to-1 mixture of the two. That is very important in SN1 reactions. That's the crux of the concept of racemization. Even if you start with a pure enantiomer, you lose that stereochemistry and you end up with a racemic product. In this other case now, we have a competition experiment. Ethanol, 0.1 molar, sodium cyanide, 0.1 molar, acetone and heat. Acetone as the solvent. We have a competition between ethanol and sodium cyanide. This is an inorganic component. It's a salt. So what is the product that you expect? Which nucleophile is going to prevail? Which is a more potent nucleophile? Why? Okay, good. What else? In terms of the acidity of the conjugate acid. So what are we looking for? A stronger conjugate acid or a weaker conjugate acid? A stronger conjugate acid? Okay, I see a no. Someone with their, can you please give us your thoughts? What are we looking for and why? And that is the trend of nucleophilicity, if you recall. The trend of nucleophilicity that we explained early on in the chapter correlates with basicity when we have protic solvents. That's something you have to keep in mind and commit to memory. When it comes to protic solvents, and do we have a protic solvent, by the way? Yes, we have ethanol. That's a protic solvent, right? And so I expect, I would have liked that all of you, and I'm going to write this now, a mixture, a cyano group plus the enantiomer. Zero percent EE. What about the rate? And this is all 0.1 molar, 0.1 molar. What about the rate of this? It's again the rate constant times the concentration of that. So again, concentration of nucleophiles does not matter in SN1 chemistry. Okay, now let us look at this over here. We have sodium cyanide. They're both negatively charged. One is an oxygen-centered nucleophile. Another one is a carbon-centered nucleophile. Cyanide, Cn minus versus ethoxide. That's where it comes into the picture. What's a stronger base, or in other words, what is the weaker acid? Ethanol is the conjugate acid of ethoxide, right? versus HCN is the conjugate acid of cyanide. Which was the stronger acid? So in this case, you don't only have to look at uh, the atoms which it is attached. You might be tempted to say uh, oxygen is more electronegative than carbon, therefore ethanol should be more acidic, correct? Based on electronegativity arguments only. That's what you would say, right? But what about hybridization? What is the hybridization of oxygen in ethanol? It's a regular oxygen. Is it sp what? sp3, I hope. Just like water, the oxygen in water, it's sp3 hybridized. Um, the oxygen in acetone with the carbonyl, it's an sp2 hybridized. So we don't have sp2. But what about the carbon and cyanide? It's sp hybridized. And so we also know that sp hybridization imparts electron withdrawing nature to the group, and so that can make it a stronger acid. And I can tell you that HCN is a stronger acid than ethanol. In other words, cyanide, it's a cyanide is what? Huh? As cyanide, it's a weaker base than etoxide, correct? And so in this case, now we go back, and etoxide wins as nucleophilic species. Rate, rate constant times the concentration of your alkyl bromide, 0% EE, racemization occurred. Okay, any questions about this particular set of problems? This is very important because we can draw a lot of conclusions that are related to both the rate of SN1 reactions versus how nucleophiles do not play a role in the rate, but also very important, do not confuse the rate of a reaction with the rate constant, K, little k. They're not the same. The rate, you simply write rate, or you can say rate of the reaction, the overall rate. This is only a constant. And that's what it is, and it's measured experimentally. It's not the same. Rate constant is something that you measured experimentally, and it is the slope of the curve that you measure the disappearance of your starting material or appearance of your product over time, and the slope, depending if it's first order kinetics or second order, there's a way to calculate rate constant. You don't have to worry about that. Just know they are not the same. But always in rate expressions, there's a rate constant associated with it, right? And the rate, if you look at the equation for the rate expression, looks very uh, like a linear y equals mx plus b, right? Where b is 0. So then y equals mx. The slope plus x in a curve or in a plot, the slope of a linear plot called m. And so in this particular case, that slope is the rate constant. And so you can have a rate constant depending on how steep your slope is. And that's something you have to measure experimentally. You will never be asked to calculate rate constant or anything. If anything, you will be giving the rate constant, and it is up to you to tell me the rate, the overall rate of the reaction. But know that for SN1 chemistry, concentration of nucleophile is not important. Yes? I just know it because I know, but you would be giving a table of pKa's. You don't have to memorize pKa's. And I would expect, what I would like you to do is to start rationalizing and see how some trends contradict each other. And so somehow we have no other choice but to look at the tabulated data. No memorization is needed. From experience, intuition, I know at toxide it's a very strong nucleophile, and cyanide is nowhere near. And also hybridization of carbon, uh, sp makes it weak base. It's more electronegative, a stronger acid, and that on its own tells me a toxin is a more powerful nucleophile. However, ethanol, when it's not deprotonated, then we have cyanide. This one is more nucleophilic because it's already negative. Yes. These two are competing against each other. So we can, yeah, this one is ethanol, but not ethoxide. There's a difference between ethoxide and ethanol. Ethoxide is already deprotonated and ready to rumble. Ethanol, it's protonated and it's just waiting for a highly reactive species to attack. But if you make it compete with cyanide, which it's already deprotonated, it's going to have no chance. However, the overall rate is going to be the same because I would like you to understand why it does not matter and the rate is the same for all of the above. Because this is an SN1 reaction. What is the rate determining step in SN1 chemistry? Carbocation formation. And after you reach that carbocation formation, then you have the competition between different nucleophiles. But the overall rate does not change whether you have a faster or more competitive nucleophile because you already passed the bottleneck. It's like this, to surmount the activation energy for carbocation formation, you already got there. The very last piece in the race, it doesn't matter if you have a Lamborghini, a Corvette, or a scooter, because they all can reach the same thing. However, the nature of your product does change. And that's what I would like you to understand here. And that's based on the best nucleophile is going to compete and grab that carbocation more efficiently. This is a very crucial topic, and I would really like everyone to understand. Okay, so if there are any questions in that sense, please do not hesitate and reach out. Now, as a summary, let us just summarize. And I think let me just go back so we can, in the previous example from the previous lecture, where we did samples, we had sodium azide versus, we have pure water that gives us the alcohol. We have sodium azide versus water. We increase the concentration. The rate didn't change, even though we doubled the concentration of sodium azide. Now we have a competition between sodium azide and sodium hydroxide, two anionic nucleophiles. And also we have water as the nucleophile. And here we get the alcohol product. So what can we conclude from this is basically in one of your slides from the previous lecture. And it's this. Once the carbocation intermediate, the rate determining step, which is the highest activation energy, for the overall rate, it doesn't matter which nucleophile. It will not change the overall rate. It would only change the rate of the second step. But the second step, as I mentioned, it's a very tiny amount in terms of the race, very small distance if you were to make an analogy of a race. The nature of the products will change, though, because sodium hydroxide is a more competent nucleophile. We have a a lower energy of activation, and so you would preferentially form an alcohol if you have sodium hydroxide. In the case that we have sodium azide and water competing against each other, sodium azide as a nucleophile has lower activation energy than water as a nucleophile. And so that's why we get preferentially the azide. But if we compete sodium azide versus sodium hydroxide wins. That's how we were able to conclude this nucleophilicity trend. Sodium hydroxide is more nucleophilic than azide, and in turn more nucleophilic than water. Doesn't it make sense? We have two anions being more nucleophilic than neutral water, and in turn N3 minus versus OH minus. If we look at conjugate acid, the pKa of conjugate acid, we can easily conclude that the stronger the base, the better the nucleophile. Okay, perfect. Clear? Clear as mud? Wonderful. Okay, so I'd like to summarize for all of you, and I would like that you do it on your own as well. I'd like that you do this on your own, because nothing short of practicing over and over and over is going to prepare you for your exams. So again, just comparing the two, SN2 versus SN1. There's a couple of parameters that we should make sure we understand and differentiate. In terms of kinetics, this is second order. The rate expression does involve nucleophile, and there's always a rate constant, not the same as rate. Do not confuse rate with rate constant. I will post this as part of our lecture notes. Just make sure you access them. The mechanism, one step. How many transition states? One transition state. Stereochemistry, backside attack of the nucleophile. We understand that in this fashion. This would be the transition state. This is the leaving group. R1, R2, R3. You should become very familiar on how to draw transition states. And this is a transition state, trigonal, bipyramidal, flat in terms of only the carbon species. It's only one step. Then this leaving group leaves, and then nucleophile turns into products. Inversion of configuration, because of this, the inversion of configuration is a result of this transition state. Because of the backside attack of the nucleophile, then you flip the umbrella. Then you end up, if you start carbon, leaving group, R2, R3, R1, then you go here with the nucleophile. This is the transition state, and then you flip the umbrella. Now your nucleophile is here, carbon, R2. What is on the back? Huh? Perfect. You got to practice flipping umbrellas. So this is inversion of configuration. This is inversion. And it's a direct result of backside attack. Now, the most important factors to determine whether or not a reaction undergoes SN1 versus SN2, it is the electrophile. This is one of the most important ones. In fact, we mentioned that this never SN2. This is a tertiary alkyl halide, right? So make sure you understand that and understand why primary alkyl halides, they react the fastest. And methyl halides, they're primary, but they're even less hindered than everything else because there's only 3 hydrogens. Okay, so now for SN1, again, if we compare the characteristics, first order kinetics, rate constant, not the same as rate, times the concentration of our electrophile. There's no nucleophile concentration involved. 2 steps. What are those 2 steps? One, or the first, carbocation formation, then nucleophilic attack. And so if you have 2 steps, how many transition states do we have? And we made sure to draw those, right? This was an SN1. How many transition states do we have? 2. Where are they? They're the local energy maxima. Perfect. So these 2 right here. Now, intermediates, how many? 1. And it is what? How many intermediates do we have in an SN2 reaction? Exam question. SN2 reaction. None. No intermediates. Single. 1 transition state. 0 intermediates. No local energy minima, which is an intermediate. Define an intermediate in a sentence. Exam question. Not necessarily. Yes, local energy minima. That is the best because, boron trifluoride does not have a full octet, and it doesn't necessarily is an intermediate of a reaction. And I'm talking in general. The definition I just gave can be applied in general. However, the full octet definition is not a general definition. In the case of carbocations, yes, it happens to be the case that it's both, but it's not always the case, generally speaking. You should understand that carbocations are trigonoplanar intermediate. They're sp2 hybridized. And racemization occurs. We just spent a great deal of time explaining what that means. Now, the trend in terms of overall rate, it's directly the opposite of SN2. And tertiary alkyl halides react the fastest. And we also spent some time explaining why. Why is that the case? We know there's going to be a carbocation, so what can you tell me about tertiary carbocations? Tertiary carbocations are more stable. This means they form the fastest. As simple as that. Any questions thus far? Yes. That's exactly what we're going to talk about this class. The trickiest thing is when we're confronted with a secondary, which can do both. And also, I can give you examples of primary that can do SN1. You need harsh conditions, that's fine. But this is what we're going to look into precisely. And that is a great question. And so I hope everyone, please give me your full attention so that we can understand this. So here, this is what we were just saying. The more stable carbocation, look at the activation energy. It's lower and it forms the fastest. This is what we call the Hammond postulate, and that's how we apply it for SN1 reaction. However, when you have less stable carbocations, they need higher activation energy, and even the carbocation is less stable, so that means it's higher in energy. But on top of that, the transition state, it's higher. That means higher activation energy. And so this is how we rationalize how we can use the carbocation stability trends in terms of determining rate of SN1 reactions. Okay, so now we are confronted with a very important topic: how to predict whether we have SN1 versus SN2. So we have four factors that you should all pay close attention to. First of all, the alkyl halide. The alkyl halide, we just talked about it. Uh, Increasing rate of SN1 reactions. This is preferentially SN1, tertiaries. Whereas methyl halides and primary alkyl halides, preferentially SN2 reactions. Secondary, it's both. And so now it's when we have to pay attention into the other factors. So first of all, look at the electrophile. Tertiary, secondary, primary. Okay, so then look at the rest. The nucleophile, strong nucleophiles. Strong nucleophiles favor SN2 reactions, whereas weak, but and by the way, these factors are not isolated. There's an interplay between all of them. So do not just assume, oh, we have a strong nucleophile, ethoxide, it's going to be an SN2 immediately. No. Hold your horses. Wait, there's more to it than that. It's not as simple. We have to look into all of the factors. So weak nucleophiles, they favor SN1 pathways. But you have to look at other factors too. So now the living group, we understand how living group ability correlates to. We talked about it earlier. In terms of halides, iodides, bromides, and chlorides, which one's the better living group? Iodide is a better living group, yes. And so we were correlating that. The living group ability, we can correlate that with the weakest base. And so this is not quite clear cut, because we can have SN1 and SN2 pretty much with all living groups. And so that's pretty much not a clear cut. But now the solvent is crucial. So polar protic solvents, they favor SN1. Polar aprotic solvents, they favor SN2. What solvent did we use for the example where we were using sodium azide? Acetone and water. How about water? What is water from those two classifications? Polar aprotic or polar protic? Of course. So that's why we were doing SN1 chemistry. And so this, I would say, is the second most important. I mean, nucleophile and solvent, if I were to rank it, I don't want to rank it because, there's an interplay between all of those. And I think we have to pay close attention into all four. And so that's what we're going to try to be doing today. Okay, so now let's just look into each of this. For example, strong nucleophile, we have hydroxide. Let's assume I have DMF as solvent. And I would really like you to know the structure of DMF. And I'm just going to draw it right here. I've shown it to you. Dimethylformamide. It's a polar aprotic solvent. And we have a nucleophile. What do we expect, SN1 or SN2? SN2. Okay, so now I'm going to be a puppet again. Please tell me how to write the product. I'm going to draw the hexagon first. What happens to this methyl here? Stays the same or changes? Stays the same, so it goes up, right? Perfect. How about so what is the nucleophile? Hydroxide. So what product are we expecting? So we're going to install the OH. How do we call those products with OH? So we're expecting an alcohol. Wonderful. So is the alcohol going to go up or down or both? We just said is now an SN2. Down. Why down? Perfect. Because the bromide was up, right? Okay, weak nucleophiles, pretty much we're limited to water and alcohols. Um, well, I'm sorry, I was confused with the solvents. No, weak nucleophiles like water and alcohols, like we have ethanol, water. They have lone pairs. As long as they have lone pairs, anything with lone pairs can be nucleophilic. Can be nucleophilic. Does not mean that everything with lone pairs is or will be, but can. In this particular case, I can assure you we need heat. We form this carbocation, and we need heat. Why? Because we need to surmount this high activation energy for carbocation formation, and then a very fast reaction to products. So what are we expecting here? I'm going to be a puppet once more. What happens to the methyl here? Stays the same or changes? Up or down? Perfect. Stays the same. What about, what are we installing here? And you know what? I'm going to draw the intermediate. Water is going to attack. Where should I put it? Up or down? Huh? Up or down? Both. Okay, wait. Perfect. How do I depict it? Do I draw both structures? I could. How else can I depict it? A straight line. And I indicate this is racemic. Straight line. No stereochemistry, but I should indicate it's racemic. Okay, now how do I make it neutral? Do not write PT. I already explained that. So let's use what we have here. Racemic plus H3O plus, right? That's what happens when water picks up a proton, forms this, and then of course we have bromide. Does that make sense? Okay, perfect. So now for the leaving group, this is what I was meaning, this is what I meant, that it's not clear cut because the leaving group ability increases the rate of both. And so it's not that easy. And we know that fluoride is less than chloride, less than bromide, less than iodide. We knew that since the beginning. But because it affects the rate of both, it's not clear cut. And so it's kind of not that useful to just look at the leaving group. So please do not just look at iodides and assume it's going to be SN1 or SN2. More important is the solvent effects. Polar protic, like water and alcohols, they favor SN1. I already mentioned, but the reason why is they're able to solvate ionic intermediates. What is the ionic intermediate? What is that ionic intermediate? Carbocations, right? It's a cation. Isn't it ionic? Yes. So polar aprotic, favor SN2. Why? Because, for example, I'm going to put a thiolate, benzene thiolate. If I put this in DMF, it's not going to be the same as if I put it in ethanol. In ethanol, we have a lot of hydrogen bonding. And in DMF, it's not well solvated. So that in turn makes it what we call it a naked nucleophile, whereas here you have hydrogen bonded nucleophile, so it's less nucleophilic. But in aprotic solvent, it's naked nucleophile, it's a stronger nucleophile. And we know that stronger nucleophiles will favor what reactions? SN2. So that is a critical aspect. This is a summary that I would like you to do on your own, but I made one for yourself. I'm going to post it as well. These are the nucleophiles you should know. Do not assume that all nucleophiles are going to be negatively charged. Some of them are going to be neutral. We have oxygen-based. We have carbon-based, nitrogen-based, like azide, amines, thiols, thiolates, neutral thiols, and thioesters. Please review these factors. I'm going to go ahead and post it. And we are hereby concluding Chapter 7. Problem set is due this Sunday. We're going to start Chapter 8 following week. Not week, following class. It's not Friday, right? Feels like it.